So let's continue to look at a few other methods. Let's first start by looking at what are called explicit time differencing, but forward and backward in time, and then we'll also try centered space and upstream space differentiating. So we looked before at the solution to this equation in terms of centered in time and centered in space. This is second order accurate in both. It was written as Cm n plus 1 equal to Cm n minus 1 minus u delta t delta x times Cm plus 1 n minus Cm minus 1 n. So this is centered in space and centered in time. But because to find solution at n plus 1 we were depending on two previous time steps, n and n minus 1, we ended up with the problem that the solution at m and n had the physical mode but also introduced a numerical mode which was propagating in the opposite direction. So for positive u, this has a waveform that's propagating to the right in positive x direction, but this one propagates in the negative x direction, as we saw before and we will see again. So can we then get rid of this problem by differencing forward in time? So then n plus 1 only depends on the previous time step n minus u delta t over 2 delta x Cm plus 1 n minus Cm minus 1 n. So we are still centered in time. We have a 2 here because here the 2 got cancelled out. This one had a 2 as well. So now again use the form Cmn to be b to the n delta t times e to the I km delta x, so amplitude times the waveform. Is it stable here? Well, if you look at b to the delta t, it's 1 minus I sigma, solving these two here, and that can be written as square root of 1 plus sigma squared to the e minus I theta, where sigma again is u delta t over delta x times sine k delta x, and then we can use sigma to define tan theta to be sigma, and the solution looks like Cmn equal to 1 plus u delta t over delta x squared times sine squared k delta x to the n over 2 times e to the k m delta x minus n theta over k. Complicated looking thing, but you don't have to think too much to see that this is always positive, this is always positive, and n is always 0 or greater than 0, so this is always positive. So as n increases forward in time, this term keeps increasing, which is bad news because that means the solution keeps growing. So obviously this is an unconditionally unstable solution, so this is not very good. So Euler forward in time is not a good idea. It is unstable for the advection equation. So let's see if we can do Euler forward in time with upstream in space. So if u is positive and the waveform is moving in the positive x direction, then the information at n plus at m is coming from the previous x or m minus 1, because the signal is propagating to the right in the positive x direction. So can we use this little fact that signal is propagating in a certain direction to do an upstream in space differencing? So obviously where you came from is upstream and where you're going to is downstream, in case that's not already clear. So let's keep Euler forward in time, Cmn plus 1 equal to Cmn minus u delta t delta x times Cmn minus Cm minus 1n. So we saw that centered space with Euler forward was unstable. So is upstream differencing going to be stable? Now write again Cmn as b to the n delta t e to the I km delta x. B delta t here is 1 minus u delta t over delta x times 1 minus e to the minus I k delta x. Well, this is easy enough. This is going to be positive if this is positive, because this is always less than 1, and this is going to be positive. So if this is positive, then this is going to be less than or equal to 1. So the condition that magnitude of b delta t, b to the delta t, be less than or equal to 1 is satisfied if the CFL criterion u delta t or delta x less than 1 is satisfied. So Euler forward in time and upstream in space is stable given that CFL condition is met, which is what we had argued for before in terms of the stability criterion. But does this give us everything we need? Well, we still have the idea that delta t and delta x have to be chosen to meet our requirements of spatial and resolution and integration in time with as big a time step as possible. It turns out that if you look at the solution from our previous central differencing, so central in time and central in space, we had this ringing which was propagating backwards in negative x while the solution was moving forward. The upstream method with Euler forward gives us a different numerical issue. It begins to have numerical dissipation or damping and dispersion. So you take the exact solution but give it this step of rectangular function, and you obviously the exact solution propagates without distorting this shape, and you want the numerical solution to capture the peak at the right time and right place in space, and not create too much spreading out or loss of the peak signal. And you can see the previous CTCS method, central in time, central in space, gave us this numerical error before of a wave-like dissipating solution moving backward and the peak being captured reasonably well. But the upstream method, which is stable if CFL criterion is met, is actually producing a damping. So in the first phase, t equal to 5, it's doing reasonably well, even though it has slightly spread the peak and damped it a little. With time at t equal to 10 and t equal to 15, it's increasing the damping and the dispersion of the peak that it should produce compared to the exact solution. So you pay a price in terms of stability with CFL criterion, but you have too much numerical damping and dispersion. So we are not home free yet. We will see next a method called the implicit scheme, which gives us stability, but then it adds to computational cost by leading to some other problem by coupling the solution at every point with every other point, and we end up with a system of equations to solve, which means a matrix has to be inverted and so on. So we are still struggling with the same thing. Even in this simple example of a linear advection equation with u equal to constant and positive, we are finding that numerical solutions are either unstable or they're stable and producing oscillatory errors propagating backward, or they are not having the oscillatory propagating errors, but they are damping and dispersing the solution and not capturing the peaks. These kind of peaks are important because when you want to predict fronts and other features in the climate and weather systems, you want to be at the right place and have the right amplitude and so on. So you want the numerical methods to capture these sharp features. Obviously, upstream method damps it and disperses it out, and central in time and central in space ended up producing this ringing that's propagating opposite to the solution. Okay, so we'll look at implicit schemes next.